Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. In this video, we'll dive deep into a powerful technique for solving second-order non-homogeneous linear differential equations with constant coefficients. We'll be focusing on the method of undetermined coefficients, specifically for cases where the right-hand side of our equation is an exponential function. By the end of this tutorial, you will be able to, first, you'll be able to find the complementary function, which gives the general solution to the associated homogeneous equation. Second, you'll learn how to choose the correct form for the particular solution based on the right-hand side of the equation and its relationship to the complementary function. Third, you'll master the process of substituting your chosen particular solution into the original differential equation to find its coefficients. And finally, you'll be able to combine the complementary function and the particular solution to form the complete general solution to your differential equation. These steps will equip you to tackle a wide range of problems in this area. So, grab your pen and paper, and let's get started. Let's first define the type of equation we're working with. A second-order non-homogeneous linear differential equation with constant coefficients looks like this. A times the second derivative of e with respect to x plus b times the first derivative plus c times y equals a function f of x. Here, a, b, and c are constants. It's second order, because the highest derivative is the second one. It's linear, because all the derivatives and the function y appear only to the first power and are not multiplied together. And it's non-homogeneous, because the right-hand side, f of x, is not zero. The complete solution to this type of equation is always a sum of two parts. The general solution, which we'll call y, is the sum of the complementary function yc and the particular solution yi. In other words, y equals yc plus yp. The complementary function, yc, is the general solution to the associated homogeneous equation, where we set the right-hand side to 0, and the particular solution, yp, is any specific solution to the non-homogeneous equation. It does not contain any arbitrary constants. So our strategy will be to solve the equation in two distinct steps. Find yc, then find yp, and finally add them together. Our focus today is on cases where the right-hand side, f of x, is an exponential function. Specifically, it will be of the form a times e to the power of bx. This means our differential equations will look like this. A times the second derivative plus b times the first plus c times y equals a times e to the power bx. A key challenge in finding the particular solution, yp, is choosing its correct form. Let's look at the rules for choosing yp when the right-hand side is an exponential. The general rule of thumb is to choose a particular solution that looks like the right-hand side. So, if the RHS is exponential, you might think to choose a particular solution that's also an exponential. You might assume yp equals c times e to the bx, where c is a constant we need to find. This works great, provided there's no overlap with the complementary function, yc. The rule is, if the exponential part of the right-hand side is not a part of the complementary function yc, then you choose yp to be c times e to the bx. But what if there is an overlap? What if a term in our chosen yp is already a term in the complementary function y? The rule is, if the exponential part of the right-hand side is a part of the complementary function yc, then our original choice will not work. In this case, we must modify our choice for yp. We do this by multiplying it by x. So our new choice for yp becomes c times x times e to the bx. Let me rephrase that. The modification is necessary when the function we would normally choose for yp is a solution to the homogeneous equation. When this happens, we must multiply our standard choice by x to ensure that yp is linearly independent from y. We must always compare our initial choice of yp to the terms in yc. This comparison step is absolutely critical and a common point where students make mistakes. Let's look at a table that demonstrates this rule with several examples. Here we have Table 4.2, which illustrates this principle. For each differential equation, we have its complementary function, yc, and the correct choice for its particular solution, y. Let's break down the logic for each example. For the first equation, the complementary function is ae to the 4x plus be to the negative x. The right-hand side is 2e to the 3x. We check. Is e to the 3x part of yc? No, so according to our rule, we simply choose yc to be ce to the 3x. Now look at the second equation. The complementary function is the same, ae to the 4x plus be to the negative x. But now the right-hand side is 3e to the 4x. We check again. Is e to the 4x part of y or c? Yes, the term ae to the 4x is there. Because of this overlap, we must multiply our standard choice by x, giving us y pi p equals cxe to the 4x. This pattern continues for equations 3 and 4. In both cases, the exponential on the right-hand side is a part of the complementary function, so the particular solution is multiplied by x. In equation 3, e to the 2x is in yc, so ypt is cxe to the 2x. In equation 4, e to the 2x is in yc, so yp is also cxe to the 2x. Equations 5 and 6 are interesting because their complementary functions involve trigonometric functions. This happens when the auxiliary equation has complex roots. In equation 5, yc is a cos x plus b sin x. The RHS is 4e to the x. We check, is e to the x a term in yc? No, so we choose yp equals ce to the x. Similarly, for equation 6, ypc is e to the x times the quantity a cos x plus b sin x. The RHS is 3e to the x. We ask, is e to the x a term in y per c? It's a factor, but not a term on its own, so we still choose y as ce to the x. This table perfectly illustrates the main rule for choosing yp. First, find yc. Second, compare the exponential term from the right-hand side to yc. If there's an overlap, multiply your standard choice by x. Let's now apply this knowledge to solve a full problem. Our first example is from the textbook, example 427. We need to determine the general solution of the differential equation. The second derivative of y with respect to x minus 2 times the first derivative minus 3 times y equals 2e to the 3x. Remember our three-part strategy? Find yc, find yp, and then add them together. Let's start with the first step. Step 1. Find the complementary function, yc. To do this, we first find the auxiliary equation. We do this by replacing the second derivative with er squared, the first derivative with r, and y with a constant. We also set the right-hand side to 0. This gives us the auxiliary equation. R squared minus 2r minus 3 equals 0. Now we need to solve this quadratic equation. We can solve it by factoring. The factors of -3 that add up to -2 are -3 and +1. So we can factor the equation into the quantity r minus 3 times the quantity r plus 1 equals 0. Setting each factor to 0 gives us our roots. R equals 3 and r equals -1. These are real and distinct roots. For real and distinct roots, the form of the complementary function is ae to the r1x plus be to the r2x. Plugging in our roots, we get yc equals ae to the 3x plus be to the -x. Excellent. We've completed step 1. We have our complementary function. Now for step 2. Finding the particular solution, yp. This is where we need to be careful with our choice. Step 2. Find the particular solution, yp. The right-hand side of our original differential equation is 2e to the 3x. The exponential term is e to the 3x. Our complementary function was yc equals ae to the 3x plus be to the -x. We need to ask ourselves, is the exponential term e to the 3x a part of our complementary function yc? Yes, it is. The term ae to the 3x is a part of yc. Because there's an overlap, we cannot use the standard choice yp equals ce to the 3x. Doing so would lead to a contradiction when we substitute it back into the equation. Instead, we must multiply our standard choice by x. So our correct choice for the particular solution is yp equals c times x times e to the 3x. Now we need to find the first and second derivatives of this expression. We'll need to use the product rule. Let's find dx first. Here's a quick memory tip. The product rule states that the derivative of a product of two functions, u times v, is u prime v plus uv prime. Let's apply this. For our function y at p, let's set u equals cx and v equals e to the 3x. Then u prime, the derivative of cx, is just c. And v prime, the derivative of e to the 3x, is 3e to the 3x. Plugging into the rule, we get ce to the 3x plus cx times 3e to the 3x. Rearranging this and factoring out ce to the 3x gives us our first derivative. d p dx equals ce to the 3x times the quantity 1 plus 3x. Or, as written in the memo, dx equals 3cxe to the 3x plus ce to the 3x. Great! Now let's find the second derivative, dx2, by differentiating our first derivative. We'll need to use the product rule again, but this time on the term 3cxe to the 3x, and then we'll add the derivative of ce to the 3x. Let's apply the product rule to 3cxe to the 3x. Here u is 3cx and v is e to the 3x. The derivative, u prime, is 3c, and v prime is 3e to the 3x. So the product rule gives us 3ce to the 3x plus 3cx times 3e to the 3x. Then we add the derivative of our second term, ce to the 3x, which is 3ce to the 3x. Putting it all together, the second derivative is 9cxe to the 3x plus 6ce to the 3x. We have yp and its first and second derivatives. The next step is to substitute these back into the original differential equation to solve for c. The equation is the second derivative, minus 2 times the first derivative, minus 3 times y equals 2e to the 3x. Let's substitute our expressions in. The second derivative is 9cxe to the 3x plus 6ce to the 3x. From this, we subtract 2 times the first derivative, which is 3cxe to the 3x plus ce to the 3x. And we subtract 3 times y, which is cxe to the 3x. All of this must equal the right-hand side, 2e to the 3x. Now let's simplify by distributing the negative signs. We get 9cxe to the 3x plus 6ce to the 3x, minus 6cxe to the 3x, minus 2ce to the 3x, minus 3cxe to the 3x, equals 2e to the 3x. Notice what happens when we combine the like terms. This is an important check that you've chosen YP correctly. Let's group the terms. First, all the cxe to the 3x terms. 9cxe to the 3x, minus 6cxe to the 3x, minus 3cxe to the 3x. They all cancel out, summing to 0. This cancellation is exactly what we expect. If our y-type choice had not been multiplied by x, this cancellation would not have happened, and we would have been stuck with 0 equals 2e to the 3x, which is a contradiction. The multiplication by x ensured we found a valid solution. Now, let's combine the remaining terms. We have 6ce to the 3x minus 2ce to the 3x, which simplifies to 4ce to the 3. This equals the right-hand side, 2e to the 3. To solve for c, we can equate the coefficients of e to the 3x on both sides. This gives us 4c equals 2, which means c equals 1/2. Now we can write our particular solution. Substituting c equals 1/2 into our expression for yp, we get ypc equals 1/2 xe to the 3x. We've now found both parts of our solution. We've done the heavy lifting. The final step is to combine our complementary and particular solutions to get the general solution. Step 3. Combine yt and yp for the general solution. Our formula for the general solution is y equals yac plus y chapas. Let's recall what we found for yc and yp. We found the complementary function yt to be ae to the 3x plus be to the negative x. And we found the particular solution y/p to be 1/2 xe to the 3. Now we just add them together. The general solution is y equals ae to the 3x plus be to the negative x plus 1/2 xe to the 3x. This is our final answer. It is a general solution because it contains two arbitrary constants, a and b. So we successfully found the general solution. We found the complementary function, carefully chose and derived the particular solution, and then combined them. The critical step was recognizing that the exponential in the RHS was part of the complementary function and applying the correct modification. Let's move on to our second example, example 428. In this case, the auxiliary equation will give us complex roots. We need to find the general solution of the second derivative of y, minus 2 times the first derivative, plus 2y equals 5e to the x. We follow the same 3 steps. First, find yc. The auxiliary equation is r squared minus 2r plus 2 equals 0. Let's try to factor this. Can we find two numbers that multiply to 2 and add to 2? No, we can't. So we must use the quadratic formula. The quadratic formula states that r equals negative b, plus or minus the square root of b squared minus 4ac, all divided by 2a. In our equation, a equals 1, b equals 2, and c equals 2. Plugging these values in, we get r equals negative 2, which is 2, plus or minus the square root of negative 2 squared, which is 4, minus 4 times 1 times 2, which is 8, all divided by 2 times 1, which is 2. Simplifying. This becomes 2 plus or minus the square root of negative 4 all over 2. The square root of negative 4 is 2i, where I is the imaginary unit. So we have 2 plus or minus 2i divided by 2. This simplifies to 1 plus or minus I. We have found our roots. They are complex conjugates. For complex roots of the form a plus or minus bi, the complementary function has a specific form. It is y sides equals e to the ax times the quantity a cos bx plus b sin bx. In our case, the real part a is 1 and the imaginary part b is 1. Substituting these values, we get our complementary function. IC equals e to the x times the quantity a cos x plus b sin x. Step 1 is complete. Now for step 2. Now let's find the particular solution, yp. Step 2, find yp. The right-hand side of our equation is 5e to the x. The exponential term is e to the x. Our complementary function is e to the x times the quantity a cos x plus b sin x. We must compare the RHS with yc. Is e to the x a term in our yk? This is a bit tricky, but the answer is no. While e to the x is a factor in every term of yk, it is not a term on its own. The terms are a e to the x cos x and b e to the x sin x. This means there is no conflict, and we can use the standard choice for yp. We choose yp equals c e to the x. This choice makes differentiation very easy. If yp equals c e to the x, then its first derivative is also c e to the x, and its second derivative is also c e to the x. Now we substitute these into the original differential equation. Our equation is the second derivative, minus 2 times the first derivative, plus 2y equals 5e to the x. Substituting our expressions for y's or p, we get ce to the x, minus 2 times ce to the x, plus 2 times ce to the x, equals 5e to the x. Let's simplify the left side. We have 1 ce to the x, minus 2 ce to the x, plus 2 ce to the x. This simplifies to 1 ce to the x. So we have ce to the x equals 5e to the x. By comparing coefficients, we find that c must be equal to 5. This gives us our particular solution. ISA equals 5e to the x. We're now ready for the final step. The final step is to combine our complementary and particular solutions to get the general solution. Step 3, combine yt and yp for the general solution. We'll use our formula y equals yc plus yp. We found yc to be e to the x times a cos x plus b sin x. And we found yp to be 5e to the x. Adding them together, we get the general solution. Y equals e to the x times a cos x plus b sin x plus 5e to the x. This is the complete solution to our differential equation. This example highlights a common point of confusion: the difference between a factor and a term. Be very careful when comparing your chosen YP with YC. Let's work through our third example, 429. This is a particular solution problem, which means we'll have initial conditions that allow us to find the specific values of our constants a and b. We need to find the particular solution of the second derivative of x with respect to t minus 3 times the first derivative of x minus 10x equals 14e to the negative 2t. The initial conditions are x equals 0 and dx dt equals 2 when t equals 0. Notice the variables have changed from x and y to t and x, but the method is identical. First step, Find x or c. We begin with the auxiliary equation, using r as our variable. The auxiliary equation is r squared minus 3r minus 10 equals 0. We can factor this into r minus 5 times r plus 2 equals 0. This gives us real, distinct roots. R equals 5 and r equals negative 2. Since the roots are real and distinct, our complementary function, which we'll call x-ACC because our dependent variable is x, is ae to the 5t plus be to the negative 2t. Now for the particular solution, xp. Step 2, find the particular solution, xp. The right-hand side of our equation is 14e to the negative 2t. The exponential term is e to the negative 2t. Let's compare this with our complementary function, xrc, which is ae to the 5t plus be to the negative 2t. Is e to the negative 2t part of xecc? Yes, the term be to the negative 2t is present. Therefore, we must multiply our standard choice by t. Our correct choice for the particular solution is xp equals c times t times e to the negative 2t. Next, we need the first and second derivatives of xp with respect to t, using the product rule. For xp, u equals ct and v equals e to the negative 2t. So u prime is c, and v prime is negative 2e to the negative 2t. The derivative dx dt is ce to the negative 2t minus 2ct to the negative 2t. Now we differentiate this result to find the second derivative. The derivative of ce to the negative 2t is negative 2ce to the negative 2t. For the second part, negative 2cte to the negative 2t, we use the product rule again. U equals negative 2ct, and v equals e to the negative 2t. Its derivative is negative 2c, e to the negative 2t plus 4cte to the negative 2t. Combining all the terms, we get d2 as p slash dt2 equals 4cte to the negative 2t minus 4c e to the negative 2t. Let's pause here. Differentiating correctly is the most common pitfall in these problems. Take your time and double-check your work. Now we substitute these derivatives into our original equation. Our equation is the second derivative, minus 3 times the first derivative, minus 10xp equals 14e to the negative 2t. Substituting in our expressions, we have our second derivative, minus 3 times our first derivative, minus 10 times xp, all equal to the right-hand side. Now let's distribute the negative signs and simplify. This gives us 4ct to the negative 2t minus 4c, e to the negative 2t minus 3c, e to the negative 2t plus 6ct, e to the negative 2t minus 10cct, e to the negative 2t equals 14 e to the negative 2t. Again, let's group the terms to see what cancels. Look at the ce to the negative 2t terms. We have 4cte to the negative 2t plus 6cte to the negative 2t minus 10ct to the negative 2t. They all sum to 0. This confirms our choice of xp was correct. We are left with negative 7ce to the negative 2t equals 14e to the negative 2t. Equating the coefficients, we get negative 7c equals 14, so c equals negative 2. Therefore, our particular solution is xp equals negative 2te to the negative 2t. We now have our complementary and particular solutions. Let's form the general solution. Step 3, form the general solution. It's x equals xeccs plus xp. So our general solution is x equals ae to the 5t plus be to the negative 2t minus 2te to the negative 2t. This is a general solution with arbitrary constants a and b. However, this is a particular solution problem, so we must use the initial conditions to find a and b. The first condition is x equals 0 when t equals 0. Let's substitute these values into our general solution. Plugging in t equals 0, we get 0 equals a times e to the 0 plus b times e to the 0 minus 0. Since e to the 0 is 1, this simplifies to 0 equals a plus b. This is our first equation relating a and b. Now for the second initial condition. The second condition involves the derivative dx dt. So our first step is to differentiate our general solution with respect to t. Again, we'll need the product rule for the third term, negative 2te to the negative 2t. The derivative of ae to the 5t is 5ae to the 5t. The derivative of be to the negative 2t is negative 2be to the negative 2t. And the derivative of negative 2t e to the negative 2t is negative 2e to the negative 2t plus 4t e to the negative 2t. This is our derivative. Now we can apply the initial condition. We substitute dx dt equals 2 and t equals 0 into this derivative. Plugging in t equals 0, we get 2 equals 5a minus 2b minus 2 plus 0. Remember, e to the 0 is 1. The 4t term becomes 0. Rearranging this gives us our second equation, 5a minus 2b equals 4. Now we have a system of two linear equations with two unknowns, a and b. From our first equation, a plus b equals 0, we can see that a equals negative b. Let's substitute a equals negative b into the second equation. This gives us 5 times negative b minus 2b equals 4. That's negative 5b minus 2b equals 4, which is negative 7b equals 4. Solving for b, we get b equals negative 4/7. Since a equals negative b, a must be positive 4/7. We have found our constants. The final step is to substitute these values of a and b back into our general solution to get the particular solution. The particular solution is x equals 4/7 e to the 5t minus 4/7 e to the negative 2t minus 2t e to the negative 2t. This is the final answer, a specific function xt that satisfies both the differential equation and the initial conditions. This example shows the full process, from finding the complementary function to applying initial conditions to get a particular solution. It's a comprehensive problem that tests all the key steps. For our final example, we will see how to find a particular solution when the right-hand side is a polynomial. We need to determine the particular solution of the second derivative of y, minus 4 times the first derivative, plus 13y equals 39x plus 14. Our initial conditions are y equals 3 and dAEx equals 1 when x equals 0. As always, we begin by finding the complementary function yc. The auxiliary equation is r squared minus 4r plus 13 equals 0. This quadratic equation does not factor easily, so we use the quadratic formula. Here a equals 1, b equals 4, and c equals 13. The formula gives us r equals 4 plus or minus the square root of 16 minus 52, all over 2. This simplifies to 4 plus or minus the square root of negative 36, all over 2. The square root of negative 36 is 6i. So we have 4 plus or minus 6i divided by 2. This simplifies to the complex roots 2 plus or minus 3. For these complex roots, where a equals 2 and b equals 3, the complementary function is e to the 2x times the quantity a cos 3x plus b sin 3x. Next, let's find the particular solution. This case is different because the right-hand side is a polynomial, not an exponential. Step 2, find the particular solution, p. The right-hand side is 39x plus 14. This is a linear polynomial. When the RHS is a polynomial, we choose wiki to be a general polynomial of the same degree. Since our RHS is a first-degree polynomial, our choice for yp is cx plus d. We must always check for overlap with yc, but here, the complementary function contains only exponential and trigonometric terms, so there's no overlap with a simple linear polynomial. The choice cx plus d is correct. Now we find the derivatives of yp. The derivative of cx plus d is just c, and the derivative of the constant c is 0. Substitute these into the original equation. The equation is the second derivative, minus 4 times the first derivative, plus 13y equals the right-hand side. Substituting, we get 0 minus 4 times c plus 13 times the quantity cx plus d equals 39x plus 14. Let's expand the left side. This gives us negative 4c plus 13cx plus 13d equals 39x plus 14. Let's write the x term first for clarity. 13cx minus 4c plus 13d equals 39x plus 14. Now we find the constants c and d by equating coefficients. This is a key technique for polynomial RHS. First, we equate the coefficients of the x terms. On the left, we have 13c, and on the right, we have 39. So 13c equals 39, which means c equals 3. Next, we equate the constant terms. On the left, we have negative 4c plus 13d, and on the right, we have 14. So negative 4c plus 13d equals 14. We already know c is 3. Substituting this in gives negative 4 times 3 plus 13d equals 14. This is negative 12 plus 13d equals 14. Adding 12 to both sides gives 13d equals 26, so d equals 2. We have found our coefficients. Therefore, the particular solution is y dkp equals 3x plus 2. Now that we have both YLK and yp, we can write the general solution. The general solution is v equals the complementary function y bar c plus the particular solution y gap. Our general solution is y equals e to the 2x times a cos 3x plus b sin 3x plus 3x plus 2. As this is a particular solution problem, we now apply the initial conditions to find a and b. The first condition is y equals 3 when x equals 0. Let's substitute. Plugging in x equals 0, we get 3 equals e to the 0 times the quantity a cos 0 plus b sin 0 plus 0 plus 2. Remember, e to the 0 is 1, cos 0 is 1, and sin 0 is 0. This simplifies to 3 equals a plus 2. Solving for a, we find a equals 1. One constant down, one to go. We need to find the derivative to use the second initial condition. This is a key step where many students make a mistake. Look at our general solution. It has a product of functions, e to the 2x times the bracketed term. We must use the product rule here. The derivative of the 3x term is just 3, and the derivative of 2 is 0, so the last term in our derivative will be 3. Now for the product rule part. Let u equals e to the 2x and v equals a cos 3x plus b sin 3x. The derivative of u prime is 2e to the 2x. The derivative of v prime is negative 3a sin 3x plus 3b cos 3x. The derivative dx at d is u prime v plus u v prime plus the derivative of our polynomial term. This is our full derivative. Now let's apply the second condition. Dx for di equals 1 when x equals 0. Substitute x equals 0 into this entire expression. The e to the 0 terms are 1, the sin 0 terms are 0, and the cos 0 terms are 1. This simplifies to 1 equals 2a plus 3b plus 3. Rearranging, we get our second equation. 2a plus 3b equals negative 2. We now have two equations. We already found a equals 1. Substitute a equals 1 into the second equation. 2 times 1 plus 3b equals negative 2. This means 3b equals negative 4, so b equals negative 4/3. We have now found both constants. Let's put it all together to write the particular solution. Substitute a equals 1 and b equals negative 4/3 into the general solution. The particular solution is y equals e to the 2x times cos 3x minus 4/3 sin 3x plus 3x plus 2. And that is our final answer. Let's quickly compare our answers from the last problem to the memo's solution. Our calculated particular solution was y equals e to the 2x times the quantity cos 3x minus 4/3 sin 3x plus 3x plus 2. The memo's solution is y equals e to the 2x times the quantity cos 3x minus 4/3 sin 3x plus 3x plus 2. You can see they match exactly. This gives us confidence in our method. Let's also briefly compare our solution for example 429. Our particular solution was x equals 4/7 e to the 5t minus 4/7 e to the negative 2t minus 2t e to the negative 2t. The memo's solution is identical. Another perfect match. This practice of comparing your work to a known solution is an excellent study strategy. It allows you to identify any errors in your process and reinforces your understanding when your answers align. Let's quickly recap what we've learned and some exam strategies. Today, we covered the method of undetermined coefficients for non-homogeneous differential equations. The core strategy is simple but requires attention to detail. First, find the complementary function. C. This means setting the RHS to 0 and solving the auxiliary equation. Second, choose the form of the particular solution, y. This is the most important step. Always compare the RHS with y and modify y by multiplying by x if there's an overlap. Third, substitute y caps and its derivatives into the original equation and solve for the unknown constants. And fourth, form the general solution by adding yc and yp. If it's a particular solution problem, you have a fifth step. Apply the initial conditions to find the specific values of a and b. For exams, here are a few tips. First, double-check your auxiliary equation. A small mistake here will invalidate the entire solution. Second, always compare yp to yc before you start differentiating. Third, be meticulously careful with product rules and negative signs during differentiation and substitution. These are the most common sources of errors. Finally, if you have time, differentiate your final solution and plug it back into the original equation to verify your answer. You've worked through 4 complex examples today. Remember to practice these steps and the comparison rule diligently. With enough practice, this method will become second nature. Thank you for watching. Like, subscribe, and continue learning with earthly teachings. Thank you for watching. Like, subscribe, and continue learning with earthly teachings.